We still have here Professor Juncheng Wei from UBC, and he'll be continue his series of talks on introduction to gluing methods and applications. Please.
Okay. Thank you for the introduction, and this is the third lecture on introduction to gluing methods and applications. So today I will continue on the infinite dimensional reduction method, and I will introduce so-called inner-outer gluing scheme, and this will be the first time we introduce inner-outer gluing scheme. And then just for advertisement for the next two lectures, for the lecture next week, I will talk about the parabolic gluing. So the inner-outer gluing applied to energy critical Fujita equation. That will be the next lecture. And the last lecture, I will discuss the inner-outer gluing scheme to Euler flow, okay, to fluid equations. So that will be the last lecture. So, all right. So let me now start the inner-outer gluing, the infinite dimensional reduction method. So this is the thing we want to prove. Okay, we just started last time. So we assume the dimension and 3 dimension. I suppose we have a minimum surface embedded minimum surface complete with a finite total curvature, non-degenerate. And then we want to construct a family for bounded solution to Ionization, whose nodal set is nice in the rescaled minimum surface, okay, like m over epsilon. So the nodal set is like that. And we'll have some further properties like non-degeneracy and the Morse index and the index of the manifold, they are equal. Okay? So this is the thing we want to prove. Okay, I want to use the infinite dimensional reduction. So we have 7 steps. So first is the property of a building block. And then I will introduce the Fermi coordinate, the first approximation, first improvement. And then the main emphasis today will be the inner-outer gluing. So how to do inner-outer gluing. And then we have infinite dimensional reduction, infinite dimensional reduction for the inner problem, and the theory of Jacobi operator and the final proof. Okay. All right, so we started with the building block last time. So the building block is the one-dimensional solution. So you take the one-dimensional solution, which is a heteroclinic connecting -1 and 2 +1. Okay, exponential decay, and this is important. Exponential decay to the constant. And we prove a non-degeneracy. So the solution actually is not only non-degenerate in 1D, but it also non-degenerate in 3 dimensions. So if you put this solution in 3 dimensions, and you still, the only kernel is double prime. Okay? So this is the non-degeneracy. Okay, so now let's start with some geometry. So we introduce so-called the Fermi coordinate. So we did, let me describe a local coordinate near the minimum surface. So first we need a precise behavior of the minimum surface at infinity. So each minimum surface, the minimum surface because of a finite total curvature, so it has a finite end. Okay, this has been proved by Osman. Okay, so each end is like a graph. Okay, each end you can write is like y1, y2, and f y1, y2. Right, this is like graph. So you can compute the normal factor. Right, you can compute the principal curvature, and also the fundamental form. Right, all this can be computed explicitly. Okay, for the minimum surface, and you can compute the metric. Okay, using the graph, and then you can compute the Laplace Bernoulli operator. Okay, which is with some is like Aij Dij and the Bidi, and the important thing we know that the curve is like Euclidean, but important thing is to know the next order term, because this next order term will be important in all our error estimates. Okay, So next, I want to describe a coordinate near the manifold. Okay, and this is so-called a Fermi coordinate. So take this manifold M, and we look at the neighborhood, okay, of this manifold, right? This neighborhood of this manifold, and we want to introduce some deformation, okay, of this manifold, okay, deformation of this manifold. So first, the simplest parameterization of this neighborhood is by this called Fermi coordinate, is y plus z and times mu. Okay, mu is the normal coordinate, right? So at each point of y on the surface, okay, and so at each point outside the surface, you look at the distance to the surface, so it's called t, and then you do project to a point on the surface, which is called y. So this is called Fermi coordinate. So y plus z mu y. So near the neighborhood of the surface, I can use this coordinate. Okay. So then we can compute the Euclidean Laplace, right, using this coordinate y and z. So y is in M, and z is the signed distance from this manifold. And this is the formula, okay? This is a well-known formula for Laplace, which is dzz plus Laplace mz. So mz is the Laplace spectrum operator of M. You fix the distance, so you get a surface. And this is the mean curvature, okay? Times dz. Now we see the mean curvature comes, right? The mean curvature comes. And you can compute the metric of mz, okay, easily because this Fermi coordinate is everything is explicit, and you can compute up to the next order. All the decay in R can be computed, okay, and the mean curvature at mz is nothing but just ki over 1 minus kiz, and you can do formal computation just to expand because z is very small, right? So it's, yeah, you see the first term is the mean curvature, and the second term is what is the fundamental form, okay, and so on. And the important thing, the third term disappear because k1 plus k2 equals 0. Okay. Okay, so we have all this nice computing. Everything can be computed explicitly, like the mean curvature. This mean curvature can be computed explicitly. Okay, and so you can we can write the Euclidean. This is the formula we're going to use. It's dzz plus Laplace m minus z a square dz plus b, and the b are no order terms in z. So b contains all the terms in z. Okay, and z square and so on, and all these terms can be computed explicitly. Now, so we'll talk about the manifold M. Now, in terms of the equation, I'm talking about the singular perturbation equation, right? This is, for this singular perturbation equation, you use this coordinate, okay? But now we need to rescale, okay? Rescale the equation. So we introduce another two transformation of the minimum surface. First, we rescale the equation by m over epsilon, okay? So become flatter, okay, right? We scale the equation. Now we want to deform the manifold. So we introduce a normal perturbation at each point on y. We introduce a normal perturbation we call the hy, okay? So at each point we introduce a normal perturbation. So this is a function, on M, is a function on M. Now this function is a priori is unknown, okay? This is the one we're going to determine. So, and this is the coordinate we're going to use, right? So we take x, origin x, we scale by epsilon y, but then we perturb the normal direction by h, okay? So this is the coordinate. This is the Fermi coordinate, right? Now under this coordinate, our Laplace, okay, you can compute. This lot of computation is DCC, Laplace M epsilon, okay? And then we have epsilon square. We have epsilon terms. There are a lot of epsilon terms, but these are mixed order terms. Now, in terms of dt, you only see epsilon square term. Now, what you see, the epsilon square is Laplace h plus t plus h a square. Now, this is the main term, okay? This is the term we're going to use, right? Main term we're going to use. Okay, so let's look at the first approximation. So take the first with the change variable, right? So first approximation is just w of t, okay? And let's put f of u is u minus u cube. So we'll plug in this one in, and what you see is the leading order term. You see these two terms. First term is epsilon square a square t w prime, okay? And then you say Jacobi operator, right? This is the Jacobi operator coming in. And then you have all the other terms, epsilon cube, epsilon square terms. But these three terms are the most important terms, okay? So first we want to get rid of this term. We can get rid of this term. And because this one only decay like 1 over r to the 4 is not good. This term is not good. So we just improve this term. We just solve this problem. Okay, just solve this problem by one-dimensional problem. Right, you solve for t w prime, and then you can you freeze the coefficient. Right, so you just add this term into the equation, okay, into the approximation. Now we do this. Now, then this leading order term disappear, and the new error, the first error you're going to see is the Jacobi operator, and then you see epsilon 4, and this term is not important. Okay, this is not, yeah, and so in general, what you get, your error will be except for this one. This one you don't know. Okay, this is a Jacobi operator. Okay. Your error is like epsilon cube, and you have a space decay. So decay in the y variable, right? Decay in the y variable, but also exponential decay in the t variable. So this is your error, okay? And this is what we're going to, this is the norm we're going to use, okay? Because of this error. Any questions, remarks?
I have a quick question. Sorry.
Yeah.
Okay. So the construction seems you assume there is a smooth manifold. Is that correct?
Oh yeah, you assume.
Right now you're assuming it exists such a manifold, so you can build such a coordinate system.
Yeah.
Okay.
Yeah.
But will you justify it in the limit?
Yeah. The edge will be just so the normal perturbation, right? So you have to justify this Jacobi operator later.
Okay, thank you.
This is the term that we will adjust the edge later. Yeah. Now, but this computation.
Can I ask the question as well? This computation, the 3D is very important, right?
Oh no, you can do any dimension.
Any dimension. Okay.
Any dimension, but as long as you know the isotropic behavior of the minimum surface at infinity. Now in compact region, I don't care. In compact region, everything is fine. The problem is infinity. Yeah.
Okay.
The problem is infinity.
Thank you.
So if you have a compact minimum surface, the computation will be much easier. You don't care about the infinity. Yeah. Now this U1 is only defined near the surface, right? In a neighborhood, right? So we need to extend this U1 everywhere, right? So, and now we assume that this minimum surface is connected and is orientable. So you can divide R3 minus the mean first into two parts, S minus S plus, and then you just You just interpret your solution with 1 on one side, with -1 on the other side. Now, because of the exponential decay, so you can do this and you can still get the exponential decay. Okay. So now, so the important thing is M is orientable, right? This is important. So we get a global solution, right? We get a global solution. But let's notice that the Fermi coordinate is only defined locally, right? The Fermi coordinate is only defined locally. We can define the global solution, but the Fermi coordinate is only defined locally. Okay, so, and because of the Fermi coordinate, the Laplace, the expansion of Laplace is only defined in a tubular neighborhood of M. Okay, so how do we solve the problem? How do we solve the problem in the whole space? Okay, so we look for a solution like this W plus phi, the usual one, and we linearize around the W, and we get the nonlinear term and the error term. Okay, so the problem is the Fermi coordinate is only defined in a neighborhood. Okay, so as I said before, so the in the outer green is to zoom in the interface. I only take care the interface we divide the problem into two problems. The inner problem, for the inner problem, I only take care of the interface. Okay, the problem near the interface, and then there's the outer problem which take care of everything else. Okay, so this is the inner outer group. So what we're going to do is we're going to use some cutoff function, and we're going to artificially introduce two problems. One is the inner problem and one is the outer problem. Okay, so you take a cutoff function, okay, near the interface. Okay, right, take a cutoff function. So, and now you look for a solution of this type with a cutoff function times some phi and some psi. Now, this psi is called outer problem. This phi is called the inner problem. Now, this psi is defined everywhere. So I use X, right? The original X. Now, this psi, this phi is defined near the interface. So I use Y and T. Okay, I use this phi. So this is the inner variable, and this is the outer variable. Okay, right? So all right. So let's now do computation. So you plug in this one, and then you have to see now which term I should put in the inner part, which term I should put in the outer part. Okay. So what I'm going to do is I'm going to put let's take some function which just because you want to get some decay. Okay. So you're going to put f prime u1 plus 1 plus some count f prime 1, for example. Put this one and times the outer. Put this one in the inner problem. Okay, and then the inner enters into outer by cutoff function. Right. This is so this is the inner and this is the inner problem. Right. The inner function. The inner function I'm going to put it in the outer problem, but with a cutoff, right? With a cutoff. So this is the whole problem. So then the idea is, okay, what I need to do is if I can find a solution which make this one equal 0 and make this one equal 0, then I can find a solution. Right? So I'm going to divide my solution into two problems. Okay. So I want to construct a solution with this cutoff phi and the psi, and the inner problem will solve. Now, for the inner problem, now because the inner problem, you can adjust the problem at the outside the neighborhood, because I don't care outside the neighborhood, right? Because my problem is I cut the neighborhood. So for the inner problem, I can pose this inner problem in the whole space, okay, without any constraint, without any cutoff, right? And for the outer problem, then I have to take care the outer problem. I was going to say some cutoff function from the inner. Okay, I'm going to say the so the inner so the outer enter into inner by this, and the inner enter into outer by this. Okay, by the cutoff. Okay, so we're going to now have two problems. One inner problem, one is outer problem. Okay, so the outer problem enters into the inner, okay, to this term. Now this term, you see, okay, why this is a good term? The problem is this term, this part has exponential decay. Okay, this is important. So this part already have exponential decay. Now the inner error enters into the outer to this. Okay, so if I can find an inner solution which has exponential decay, then this part will be very small. Okay, right? This part will be very small. So the operator for the inner problem is the DTT plus Laplace m, plus 1 minus 3. I should use W square. Right, and the basic operator for the outer problem is just Laplace minus 1. Okay, it's just Laplace minus 1 for the outer problem. Okay, so I have one problem I start with, Alan Kang. I divide into two problems, the inner problem and the outer problem. So this is the inner outer green. So the inner outer green, they occur in this region. In the region, in this cutoff region. This is where the inner and the outer okay enters. Okay, so all I need to analyze is the behavior of my solution near this cutoff part, near this part. If I have a good estimate for solution near this cutoff region, then I can do the coupling. Okay, so now for the inner problem, I can use Fermi coordinate. Right? I can use. So I have to adjust the operator B, but basically I can just do the computation for the inner problem using the Fermi coordinate. Okay. Now I just remember I have two coupling. The outer enters into the coupling in the inner in two parts. One is in this part, and also the nonlinearity. Right, the nonlinearity also enters. Okay, right. Okay, and the error is like has this decay as well. Okay, so because the error has this decay, so I'm going to design some norm, right? Which is exponential decay in t, algebraic decay in y. This is what okay. So I'm going to use the local W2P and weighted local W2P norm. And the reason is because all my error contains all the second order derivatives. So I need to use W2P estimate, local W2P, but weighted local W2P. So this I have a decay in y and decay in t. Okay? And for the outer problem, I also use a weighted W2P. Okay, but the outer problem I only care the infinity. I don't care in the boundary region. I don't care. And so for the normal perturbation H, I have not tell you what is H is. So the H, I'm going to use some kind of weighted W2P, W2P, and some strange norms. And because the problem is the error terms. Okay, this is some kind of the error term. Okay, so I have done the first step. I put the I divide the problem into inner problem and outer problem. Okay, so what I'm going to do to solve the inner outer coupled system, so I fix the inner problem first. Suppose my inner problem I have a good solution for the inner problem. Then I want to solve the outer problem first in terms of the inner problem. Okay, and now suppose I already have some decay for the inner problem. So then with this cutoff will give me further smallness. Okay, further smallness. So and then so I can and this, as I said, this operator is basically like Laplace minus 1. Okay? It's like Laplace minus 1. So I can solve phi the outer problem in terms of the inner problem. Okay. And so we can solve, this is the operator. So I gave an inner problem, I can solve the outer problem, okay, easily. And I have all the good estimate for the outer problem if I have good estimate for the inner problem, okay? And also this operator is Lipschitz, okay? Satisfies some Lipschitz property, okay? This also needed, okay? So now I plug in the outer problem into the inner problem. Okay? Then my inner problem becomes nonlinear but non-local, right? Because you solve the outer problem, you think this outer problem solved globally, right? So this is a non-local. There's a non-local problem here. Okay. Right. So now all I need is to solve this inner problem now. Okay. This is inner problem now. But this inner problem is nonlinear and non-local. Okay. So in my second step, I solve the outer problem, and then I plug in the outer problem into inner problem, and then all I need to do is to solve this linear problem. Right? Now this linear problem is defined everywhere. There's no neighborhood, no Fermi coordinate, nothing. Okay, right? It's defined everywhere, and this is what I want to solve. Okay, so this is the problem I want to solve. So how to solve this problem? So we use the infinite dimensional reduction to solve this nonlinear and non-local problem. All right. Okay. Any questions so far? Okay. So let's see how we solve this inner problem. Okay. Now, what do we need? We want to solve this problem. Okay. We want to find a solution. Not only we want to find a solution, but also we want a solution with fast decay, with both decay in space and in T. Right? We need to find a solution like that, because the inner enters into outer in the cutoff region. So we need to estimate the behavior of phi near the cutoff region, and we need some smallness. The smallness will come from the decay. Okay. Okay. So how to solve this reduced inner problem? So as before, so we solve this problem in 2 steps. Again, now this problem is defined in m epsilon times r. Okay, so this is there's no cutoff, nothing. All the cutoff, everything is in the nonlinear term now. Okay, it's in the nonlinear term now. So so the first step, we want to solve. We want to fix the h, the normal perturbation. And we want to find phi and c. C will be a function of y now, okay? So that we can solve the inner problem up to the c times double prime. But then we're going to impose this orthogonal identity condition at every point. At every point on the surface, we impose one orthogonal identity condition. So at every point on this manifold, we impose a orthogonal identity condition. So this is infinite many orthogonal identity conditions, right? So this is the first step. We want to solve this problem, okay? And then the second step, once you solve this problem, you want to make this constant. This is no longer constant, right? This will be a function. You want to make this function equal 0. So you want to find a true perturbation h, so that this becomes 0. Okay. So now how to solve the first problem? Okay. So now we have infinitely many orthogonal identity conditions. Right? Infinitely many. Any point I have a orthogonal identity condition. Every point. Okay. So as before, we first consider the linear problem. Okay, it's a simple linear problem. So we take a dtt phi plus Laplace m epsilon phi plus f prime w phi, and equals some right hand side and plus some Lagrange multiply and equals 0. So this will be a toy model. This will be like a linear problem. Okay, the linear problem. Okay, and we want to find a solution. So we want to find a solution to this problem. Okay, with infinite many orthogonality conditions. Now, first of all, as before, okay, the C can be controlled by G. And if you can find a solution and just integrate both sides, multiply by W prime and integrate, and you can get your C. So C is basically controlled by G. So you can assume C equals 0. We can just assume C equals 0. Right? So in order to solve the projective problem, so we need to devise a theory to solve the problem where the right-hand side will be quantitatively close to our error. So the right-hand side should have exponential decay in t and algebraic decay in y. Okay, this is the kind of right-hand side we're going to deal with. So, and we also want to find a solution with the same type. Okay, we want to find a solution with the same type. Okay, so this is as in the finite dimensional reduction, we first need the upper estimate. Okay, and this is the upper estimate. This is the basic upper estimates. With this upper estimates, we get a W2P estimate. Okay, so and basically we're saying that if you have a G, okay, which decay like this, and then we want to find a solution phi also decay like this. Okay, so this is what our aim. We want to find a solution with decay in t and decay in space. Okay, we want to find both decay. Okay. Well, now for later purpose, for our existence, instead of solve the problem in the whole with the whole space, the M. Now we want to solve this with the bounded M. Okay, this is just before our existence because so that this manifold is bounded. Okay, so we have some kind of compacted. Now, so we take a big ball. Okay, take a big ball and then we look at this. A variation of the problem, with the differential condition on the boundary of the surface. Okay, so and we want to get the upper estimate for this problem. Okay, so and we want to have decay in space and the decay in time. Okay, so we just need to get the L infinity because once we get L infinity by local infinite estimate, we can get W2P. So we prove by contradiction, right? Like before, like in the finite dimensional reduction. And we assume the estimate does not hold. So we can find a sequence of epsilon n go to 0 and a sequence of Rn, the ball goes to infinity, and the sequence of Gn and sequence of phi n, and satisfy this property. Okay. So and because I have bounded domain, based on a bounded domain, so we assume by contradiction. So we assume that I have some point Yn, I have a point Tn, where this is okay. I should write a plus sign. So this should be a plus sign. Okay, greater equal to 1/2. Right? Okay. I want to catch a contradiction. Okay, I want to get a contradiction. So we consider 3 different possibilities. First is Epsilon Yn. If this is bounded, okay. First is this is bounded. So if we go back to the original variable, the original variable x is bounded. This is the first case. The second case, this is bounded. This goes to infinity, but it's not close to the boundary, right? The boundary. And the last case is close to the boundary. Okay, it's close to the big ball. Okay, close to the big ball. So let's look at each cases and see what kind of a limiting problem we get. Okay? Now the simplest problem is this one. This is bounded. Okay, so if your block point is bounded. Now, if a block point is bounded, you can just use local coordinate. Right? Suppose the block point goes to some point, and then you can just use the local parameterization, right, of the manifold, and then you do this with scaling. Okay, so a local change of variable. Okay, and so the change of variable now what's Tn? So the Tn may also go or be unbounded. So let's assume Tn is also bounded. Okay, and then you do this change of variable. Okay, and you look at the local equation becomes this. Okay, now so this Gn will go to 0 because by our assumption, right? And so what is the limiting problem? So the limiting problem will become a fixed, okay, coefficient problem. Where coefficient is fixed, and plus dtt phi plus f prime w phi. Okay. Now and you can by rotation, okay, by some rotation, and this will just become Laplace by rotation and stretching, and this become Laplace. But then, so this become a Laplace, but then this is a problem in R3, right? And by the non-degeneracy result, we already proved the non-degeneracy. Any problem in R3, bounded solution R3, right, is automatically it must be C times W prime. Okay, but we have this orthogonality condition, which we can take a limit, and the reason that we can take a limit is because W prime decays exponentially. Now we should do this carefully because we do this, the phi n, okay, we have exponential growth, but what the exponential growth will be smaller than W prime. So you can take a limit. Okay? So you can take a limit and you get a contradiction. So this is the simplest case. This is a case when your block point stay local, okay, bounded, and your Tn is also bounded. Okay, so the normal distance is also bounded. Now, in the second case, subcase, suppose Tn is unbounded. Okay. Now, if Tn is unbounded, now let's do a scaling around the Tn. Okay. This will scale around the Tn. So we scale around the Yn, and we scale around the Tn. So we look at this scaling. Okay. We look at this scaling, and you see that with this scaling, you have some convection term will come in, right? Because you can Tn, plus T. You multiply your equation by e to the sigma t, and you have Tn plus T. So what you're going to get, the limiting problem, you're going to get this type of limiting problem. You have some convection terms, and Laplace still get the Laplace. But then, because your T goes to infinity, so it's either, so this goes to a constant, either +1 or -1. So you're going to get a constant minus sigma squared. So this is a linear problem with some convection term, and the phi tilde is you have exponential growth. Okay, it's exponential growth, but you can still use maximum principle to exclude this case. So in this case, you don't need the orthogonality condition. You just use the maximum principle, and this will get this equal 0. Right? So I have discussed the two scenarios. The first scenario is Tn bounded. So if it's bounded, then you get to an equation in the whole space, and you use the non-degeneracy result. Now, if Tn is unbounded, and you get a linear equation in the whole space, you just use maximum principle to exclude the solution. Okay, so this is the first case where the epsilon yn is bounded. Right? Now, if epsilon yn is unbounded, but away from the boundary, okay, and you can do the same, okay. So if it's unbounded, means you will go to one of the end, but at one of the end, all these ends are logarithm, okay, are catenoid. So you can the limit, the Laplace spectrometry becomes just a Laplace, okay, becomes just Laplace. And again, if Tn is bounded, Now in this case, we should be careful because we also want to get algebraic decay in Y, and this is important because I want to get algebraic decay in Y. So you want to rescale your problem in this with also this algebraic decay, because you want to get algebraic decay in Y. So you rescale the problem and you compute, and because the small parameter epsilon here, and you compute, you also get an equation in the whole space, and then you use also organic condition to exclude this case. Now this computation is important because it shows that the algebraic part we'll compute the Laplace, compute this. The algebraic part actually disappeared. Okay, and this is because your problem is basically is like a Laplace -1 at infinity. Okay? And in the last case, and if your point is close to the boundary, remember we take a big ball, right? Close to the big ball. Now, in this case, you're going to get either a half space problem, right? And in this case, you just reflect your problem, yeah? And you get a whole space problem to reflection because you take the diffusion boundary condition. Or you get a problem, a linear problem with convection term, and which is either in the half space or entire space. And again, you just use the maximum principle to exclude both cases. Okay, to exclude both cases. So this is the RP estimate. So I have so we divide. We want what we want to get. We assume we have a solution. We want to get a solution with decay in space and decay in time. Decay in t, so not t. Okay, in the normal direction, exponential decay in the normal direction, algebraic decay in the along the m. Okay, along the manifold. So this is the main estimate. We have the RP estimate. Are there any questions, remarks?
So you get the L3 norm, right? But you still have to control the L2 norm.
No, we use the local W2P.
Oh, you use that? Okay.
Yeah, we don't use global. Yeah. Local W2P with weight. Yeah. And this is important because we need this to handle all the non-local terms, right? Because the second order derivative appears in B in the B operator contains a lot of second order derivative terms which are smaller, carries a epsilon in front. And so we need a local W2P. We need to use local W2P. So once we have RP estimates, then the existence just follow from the RP estimates. So we first do existence in MR, okay, in a big ball, okay, and so you write this in some kind of weak form as before. There's a weak form, and now weak formulation. Now, if you with the B, you can use Lax diagram, because you don't need the problem to be self-adjoint, because your leading order operator is corrosive, and because the coadjunctive form, this is the leading order, the coadjunctive form. The coadjunctive form is corrosive, and because we have the orthogonality condition on each of at each y, I have an orthogonality condition. So so I have this corrosiveness for the operator, okay, for the coadjunctive form, and then you just use Lax diagram or Riesz representation, and you get a solution. Now, once you get a solution, you only know the solution is bounded, and then you can use maximum principle to show the solution actually is has an exponential decay, because the right hand exponential decay in space and in T. Okay, and then you have the local W2Ps. I will not discuss this. So once we solve the linear problem, then we can solve the nonlinear problem easily just by sort of contraction mapping. But of course, here we have a lot of things. We need to do a lot of things because we need to analyze the Lipschitz character of the nonlinear terms. Right? Now, the Lipschitz character, remember, the nonlinear terms carries all the second-order derivatives. The lot of second-order derivatives, lot of non-local terms appear in the non-local term. Yeah, in this nonlinear term. And remember that this end of phi also contains the psi of phi, which is from the outer problem. So we have to look at the Lipschitz character of this n term very carefully, because these terms are very delicate, because it's quite non-local. Okay, all the non-local terms are appeared here. And okay, so all this you do not have computation, and you do a contraction mapping, and so you can solve the non-local, the nonlinear problem, and you can get a solution which behaves like Epsilon cube. Okay, and this problem also is Lipschitz. Okay, in H, Lipschitz in H.
What's H here, by the way? So,
H is the normal perturbation.
oh, okay.
It's the normal perturbation of the manifold. Okay, you fix H, you solve a phi, and then you want to show the phi is also Lipschitz in H. Okay? So the difference is the H norm, and this is the Lipschitz. Okay, yeah. Okay, so so in order to conclude the proof of the theorem, the last thing we need is to adjust H. We now need to adjust H. Okay, so we need to adjust H in such a way that the C of Y equals 0, and so you can compute the C of Y. Okay, a lot of computations, and there's a lot of nonlinear terms. And what you're going to say is the leading order term for C of Y is the Jacobi operator. And so you get the reduced problem is a Jacobi operator. You have to solve the Jacobi operator, but the G of H contains a lot of non-local terms, right? Lots of non-local terms, and local and non-local terms are contained in G of H. So this is the problem we need to solve. Right? This is Jacobi operator. Right? But even this problem is not so direct. Why? Because our Jacobi operator is not infallible. Okay, we know that there are 4 bounded kernels. Right? We know that the Jacobi operator has they have 4 rigid motion, translation and rotation. So even at this stage, we have to use a finite dimension reduction again. We can only solve this problem up to some Lagrange multiply. Okay, up to some. Again, we have 4 Lagrange multipliers. Okay, C1, C2, C3. So we cannot solve the Jacobi operator completely. Okay, this is because we have 4 bounded kernels. We can only solve up to 4 Lagrange multiply. Okay, this is okay. And so to solve this problem, we use again the finite dimension reduction in the first lecture, and we get some like RPA estimates for this problem as well. So I will not. This is the RPA estimates for this Jacobi operator. Okay. Okay. Summary. So what have we found? Okay, we found the H, and we used the inner outer green, right? So we found I in the problem phi, outer problem phi, and we found IU, okay, and it solves the equation. But then we have these 4 terms on the right hand side. These 4 terms on the right hand side. Okay, so these 4 terms we need to we need to say that these 4 terms should be 0. Okay, so in the last step we prove that all this constant, you have these 4 terms, but these 4 terms in reality should be all be 0. Okay, and why? And the reason is your left hand side problem is has 4 invariances. Okay, so and so we also have the property of our solution. Okay, all this we need to use. Okay, and so we use the invariance of the Ionization equation, which is we have translation invariance and the rotation. So what we do is we test the Ionization equation against the generators of the rigid motions, okay, the translations and the rotations, and then important thing is to use the so-called balancing formula for the minimum surface. Right? So okay, this and then from this we found a system equation for the Lagrange multiply, and this Lagrange multiply will be 0. So and finally, and this we finish this part of the proof. Now for non-degeneracy and for the Morse index estimate, there will be a lot of computations and a lot of proofs. I will not talk about this. You can look at the paper to see how we prove estimate the Morse index and how we prove the non-degeneracy. But all this depends on the explicit and computation. We know the solution quite well near the interface. Okay. So let me summarize the inner outer green. And so the inner outer green is a efficient method in dealing with high dimensional concentration phenomena. And the RPA estimates, we have 2 parts, one the inner estimate and the outer estimate. And the outer estimate gains some regularity, and then the inner estimate. And this is an important observation. And to solve the reduced problem, we need to use techniques from differential geometry and the Jacobi operator and so on. So this is the scheme of inner outer green mechanism. This is what I talk about today. So we'll take the Ionization equation, and we divide the Ionization equation into an inner problem and into an outer problem. All right. So with what we do, we fix a solution to the inner problem, and we solve the outer problem first, and we plug in the outer problem into the inner problem, and so we just need to solve the inner problem. Now, how to solve this inner problem? We use infinite dimensional reduction to solve this inner problem. And finally, using the infinite dimension reduction, we get a reduced problem about Jacobi operator. And we use the theory from differential geometry, minimum surface theory, to solve the reduced problem. So this is the whole, the inner outer green mechanism that I talk about today. I think maybe I stop here today, and maybe next time I talk about some applications of this in the outer green, some new developments of in the outer green. Then I will talk about the in the outer green for the parabolic critical parabolic problems. Yeah. Okay, so maybe I stop here today. And any questions, remarks?